just like
I'm running back pro with that right now.
I did like video and the inorganic chemistry.
Oh, awesome. Fun idea, Dave.
All right, hey everyone. I want to recap 3.1 and 3.2. So technically, we're still supposed to be going over 3.3, and we will. But we have 3.1 to 3.4 for this upcoming quiz, which is next Thursday. And every day, even though we haven't reached review day, I want to be able to do at least one problem from each section leading up to our new section, so that everything for 3.1 and 3.4 will just feel familiar and won't feel like you're a week removed from going over the previous topics. So this is off of the 3.1 worksheet that we did. We did number 21. I want to review the concept, review the process, and then let's do 2 more problems. And then we can review a little bit of mean value theorem and Rolle's theorem. And then we'll do 3.3, which is first derivative test. So the recap, let's see, am I recording? Sorry. Okay, recording here. All right, so the recap with extreme value theorem, we're finding highest and lowest points on the graph, right? And we know that whatever endpoints they give us, we have to test those endpoints, because endpoints could end up being the highest or lowest points. But we also need to involve critical points. And the way we get to critical points is we find the derivative first. And once we find the derivative, we're going to look at the numerator and the denominator separately. And if both locations gives us values that are valid, then we're going to use all those values in our determination to see if they are going to give us max or mins, highest or lowest points. So we did that yesterday with 21. We always have to establish it's continuous, that there are no breaks in the graph. The nice thing about polynomial is that it's always going to fulfill those conditions, so we can say our function is continuous. We go to the derivative, we set the derivative equal to 0. We solve for x, and when we solve for x, we find our critical points, and our critical points land nicely within our interval. And then we test our endpoints. Highest endpoint is we test our endpoints and critical points. Highest value is your absolute max. Lowest y value is your absolute min. All right. So let's look at 20. If you don't have this sheet, you can kind of just write this down and write it down on a separate sheet. So our function is cube root of x. There's only one issue we have to consider is continuity. The nice thing about odd roots is that we're not going to have any issues with negative numbers inside the radical. We can have negative numbers and be okay. It's only even roots like square root or fourth root or sixth root, then we can't have negative numbers inside. But if it's an odd root like third root, cube root, or fifth root, we can have negative numbers. So there's no denominator either, so we know our function is continuous, no issues there. Okay, so our function is continuous on the closed interval. Okay, so what's next? We have the endpoints. Now we need to find the derivative, right? We are gonna plug in the endpoints, but we're gonna save that for the final step, right? So we're gonna find the derivative. To find the derivative, we're gonna have to get this ready. rewrite this as x to the 1/3. So our derivative using power rule. I'm going to push this x down to the denominator. All right. Where do we look for critical points? Okay. In this case, denominator, but generally speaking, we look in both locations, right? We look in the numerator, we look in the denominator. Doesn't mean that we're always going to find it, but at least I want us to just keep reminding ourselves that we have two locations to look at. And nothing from numerator, right? 0, that doesn't make sense. But if I set the denominator go to 0, I'm going to get something here. So divide by 3, raise both sides to 3/2. I solve for x, I get x equals what? X equals 0. Okay, we found a critical point, but I want to connect this with something visual here. Because where it's coming from, can you guys visualize what's happening at 0? Or how would you describe the behavior of this graph at 0? Yeah, vertical asymptote, slope undefined. Okay, slope is undefined here. Oh, sorry, not vertical asymptote. It is slope undefined. It's a sharp turns. The reason why we don't say vertical asymptote is because we've already established our function is continuous. And the critical point is coming from the denominator of the derivative, not the original function. So if it came from the original function, then we can say that there's an issue with continuity, there's a vertical asymptote or hole. But this is a slope undefined, a sharp turn. So maybe the graph looks something like this. Because of the fact that, right, if we work backwards here, if I plug 0 in for x, I'm going to get 0 in the denominator. 1 over 0 is what? Undefined. So undefined derivative means undefined slope. Undefined slope means like a sharp turn. Okay. Now, sharp turns are not going to be an issue for EVT, right? Extreme value theorem, it's okay if we have a slope undefined, because the purpose is not to guarantee a slope. The purpose is to find the max and mins. So slope undefined is okay. Okay. But I want to always try to connect our process with a visual idea so that we're not just going through a process without understanding what we're finding. So we have a critical point. It's a sharp turn. How do we know whether to keep this critical point to test or not? Interval, right? We always go back to the interval. That's the case with extreme value theorem, case for mean value theorem, case for Rolle's theorem. We're always going to go back to the interval anytime we find a potential solution. So 0 is safely between -8 and 8. So we have 3 points to test, right? We'll test -8, we'll test 0, we'll test 8. Okay, so they all go into the original function. All right, so -8 goes into the original function here. So cube root of -8 is -2. Right? 0 into the original function, I get 0. 8 into the original function, I get 2. So we can make our conclusion based off of these numbers, right? We're looking for highest y value, we're looking for lowest y value, so we can say absolute max is two. Okay. And I want us to put the emphasis at the y value. I don't want us to say 2, 8 order pair, or sorry, 8, 2. The emphasis is at the y value. If you want, you can say at x equals 8, but I'm really after the y value. Okay, absolute min, lowest y value, -2. Okay. Any questions with 24? Okay. Okay, let's look at 28. 28 is not a polynomial. It's not a radical. It's a rational function. So we may have some issues with continuity. Okay. So where do we look for potential continuity issues if we're looking at a function, or if we're looking at a f of x function? Where do we look for continuity issues? Denominator of the original function, right? So for continuity issues, or to find continuity issues, set the denominator, equal to 0. Because if you set the denominator equal to 0, you're then looking for vertical asymptotes or holes, right? And those are going to give insight as to whether we're going to have issues with continuity with our interval. So we look at the denominator, we see t plus 3, so we set t plus 3 equal to 0, we get t equals what? -3. So maybe it's easier if I use x here, but what's happening at x equals -3? Vertical asymptote, okay. Now, if t plus 3 was also in the numerator, if we can cancel out a t plus 3 from the denominator, then it's a hole. But I want you to visualize the fact that there's a vertical asymptote at x equals -3. Now, we know there's a break in the graph. Is this automatically going to negate our extreme value theorem, or how do we proceed from here? Right, we go back to the interval, right? There's only one break in the graph, but just because there's a break in the graph doesn't mean that it's going to affect our problem. We go to the interval and see if there's an impact. -3 is outside the interval. So there's only one issue, and that issue is outside, so we know our interval is safe. If our interval is safe, we can make our continuity statement, and then we can move on with the problem, right? Our problem can still stand. Okay, so conditions out of the way, we know we're good. We know extreme value theorem is going to stand. Okay, what's next? Find the derivative, right? Now look at how this is set up. What's involved in our derivative process? Quotient rule, right? I know quotient rule is from chapter 2, but it's not going to go away. We're going to see quotient rule, chain rule, product rule in chapter 3. We'll see it in chapter 5. We'll see it next semester. So It's not going to go away. Okay, so H prime F prime times G minus F G prime all over G squared. F prime is 1. Back to F, G prime, G squared. Right? We got to clean this up, but careful, we don't clean up this way, right? We don't take this out. You got to just combine your terms up top. Okay, we have our derivative. How do we proceed from here? Look for what? Critical points, okay. So critical points, we got to look for in the numerator, look in the denominator. So anything from the numerator? No variable, right? So we looked, we didn't find anything, okay. How about the denominator? If we solve for t, we get t equals -3. We know -3 was a vertical asymptote, and we also know -3 was outside the interval, so there's nothing that's going to impact our next step, right? So for our purposes, no critical points, right? So if we have no critical points, does that mean that EVT doesn't apply and we can stop the problem? Yeah. So at the very least, right, as long as it passes the continuity condition, we know that there's a max and min, right? It's just that we may or may not have additional critical points to test, but we look for it. We didn't have any critical points, so we know our max and mins are just down to two endpoints, right? One will be the max, and the other will be the min.
Mr. Yang,
Yes,
how is it continuous if it has a vertical asymptote?
that's true, right? You're right. It's not continuous everywhere, right? There's a vertical asymptote, but we only care about the what?
Domain, or like the
interval.
set of the interval, yeah.
That's right. So is that vertical asymptote going to affect our interval?
No.
No. So that's why we can say we have continuity on the closed interval, and that's all we care about.
Okay, that
Does
makes
make
sense. Yeah, it does make sense.
Okay, good. Yeah, so we always want to look for vertical asymptotes because we want to just do that check, right? We want to see, is it going to impact our interval? If it doesn't impact the interval, we can continue with the problem. But if it did impact the interval, then we stop the problem. We say our function is not continuous, EVT doesn't apply, and there's nothing more to do. Okay, all right, good question. But no critical points. We know we're going to test the endpoints. One endpoint will be the max, one endpoint will be the min. We're just looking. So we're down to two numbers, right? These are the only two numbers that's we have to consider. Okay, so absolute max is absolute min is -1/2. Good. Okay, you can include the values, but the focus is on the y value, right? Okay, any question with extreme value theorem? Let's look at the next page, which is practice problems involving mean value theorem. Let me recap the big idea with mean value theorem, and we'll do 2 examples, and then we will start 3.3. Okay, now mean value theorem is different from extreme value theorem, right? Extreme value theorem, we're just trying to find the max and min. We don't care if the graph has a sharp turn. We just want the graph to be continuous, at least between the endpoints. And then we go through the process, we find max and min. But mean value theorem is different, right? Mean value theorem, we're not trying to find the max and mins. We're trying to find a location that has a specific slope. And how do we find that specific slope? The problem will give us 2 endpoints. We're going to plug those endpoints into the function. We're going to find the slope. And then we're going to use the derivative to help us connect that slope with the location. So we always are going to look at the endpoints to gather information about the slope. It could be slope of 1/2. It could be slope of 6. It could be slope 0. It could be slope 10. But after we find that slope that we're targeting, we know that somewhere between there also will be that specific slope. Maybe more than one location, but at least one location. Okay. So, but the conditions are a little more involved. Okay. Here we do need a smooth curve. We can't have any sharp turns because if we're trying to guarantee a slope, we have to make sure that our domain, our interval, is not going to have any sudden sharp turn, right? All right, so let's look at 39. All right, mean value theorem. We know that we're dealing with polynomial. No issues with continuity and differentiability, so we can just go ahead and make that statement. Brackets for continuity, parentheses for differentiability. Nothing to worry about with continuity and differentiability, so we can jump directly to our formula. Okay, so what do we do first? Find the y values, right? I think that's good, yeah, because that is the step I want us to do, find the y values. I do want to point out that some students want to find the derivative first, and I would advise against it because if you find the derivative too early, you may be tempted to plug these x values into the derivative, and that's not part of our process, right? These endpoints are not going to be involved with the derivative at all. So, but I feel like if you're looking at f prime, you may get thrown off, and you may want to try to involve that f prime. Yes.
Are those numbers always going to be the same, like the f of s continuous and the differentiable?
Yes. These will always be the same, and it's always going to be brackets for continuity. It's always going to be parentheses for differentiability, and we're always going to use whatever. Yeah, that's right. But for the next problem, we're going to see that not every problem can we just jump to this conclusion so quickly. We may have to do a little bit of work to get from here to here, but because it's a polynomial, we can jump to this without having to do any additional checks. But yeah, it's in the end, if we want to move on to this step, we have to claim these as true. Okay. All right, so we said no derivative yet. We're going to focus our attention on trying to find the y value so that we can find the slope. So we'll find f of -1, find f of 1, Okay. -1 then for x, we get -1 minus 2. Okay, plug 1 in, we get 1 plus 2, which is 3. Okay. Find the slope, right? We're trying to figure out what number we can place for this location here. Change in y over change in x. So we have the slope. Okay. What's next? We have this number now, right? Now we can find the what? Now find the derivative. Okay, so I think if we do this first, get this out of the way, then we know we won't get thrown off by putting these values in the wrong slots. So now let's find the derivative. So think about this, right? We have the slope, but we need the derivative to help us map where that specific location is where the slope occurs. So we find f prime, power rule. Okay, now how do we involve the f prime with the slope here? Right, so the 3 will go here, right? The 3 doesn't go for x. I want to make sure that we don't put in the wrong slot here. We know the slope. We're trying to find x, so we don't want to lose that x that we're trying to find. Or you can do this, right? You can just 3x squared plus 2 goes here, and then the slope value goes here. Set them equal to each other. Okay. We want to find a specific location that has a steepness of 3. Subtract 2 from both sides. Okay. Take the square root. So any solution that we find, we always have to go back and do what?
Check.
Yeah, check, right? Goes back to the interval. Same thing with EVP, same thing with mean value theorem. Every time we find something, we always go back to our interval. So it looks like these are both safely inside the interval. So we're going to keep both our solutions. We have 2 locations on the graph where we're going to see a slope of 3. Okay. All right, any questions with steps from mean value theorem?
Are you setting f prime of x equal to m? Or to f prime or
say
f
it again?
Are you setting f prime of x equal to m or equal to f of 1?
Oh, I'm setting it to m. Yeah, so these numbers are just coincidental. Okay. Yeah, this number is going to go here.
All right.
Good.
Thank you.
Let's look at 41 here. So far, we haven't had to do any work from function to the conditions, right? We didn't polynomials. We just make that statement. There's no additional checks. But 41 is going to require some additional effort just to get past our conditions. So I want to talk about this radical function involving cube roots. When you have a function that is in this form, you may have some issue with differentiability. The graph may have some sharp turns. Okay. And a sharp turn doesn't mean that it's going to negate our process, but we want to see if this is going to impact our differentiability statement. Right? We want to know, is the sharp turn going to cause our interval to all of a sudden have issues. But initially, we know cube root is not going to have an issue with our continuity statement. There's no variable in the denominator, so we can state our function is continuous. We know we're good there. But because of the nature of this function, we know that there is going to be a potential issue with sharp turns, with slope undefined. So let me write a note here. Okay. To seek out sharp turns or undefined slope, we're going to look in the denominator of the derivative. So this required more work than before, right? Before we just had to make that statement. But now we know that there is a sharp turn. We're going to look for that sharp turn and see if it's going to impact our interval. If it doesn't impact the interval, we can continue with the mean value theorem. But if it affects the interval, we stop the problem and we say our function is not differentiable on the open interval. So just to do this check, we have to go to the derivative and look at the denominator. But just for this type of problem, this is the only type of problem that we're going to see that has this behavior that we got to worry about. So f prime, we go through power rule. We clean up. All right, do we see something in the denominator here? Okay, we do, right? So we're going to set that equal to 0 to find the location of that slope undefined. So I want to point out, we did the same thing for extreme value theorem. But when we did it for extreme value theorem, we did it because we were looking for a critical point. But now we're doing it because we want to know if it's going to impact our interval, our condition. So we're doing the same process, but it's different. It's a different purpose, right? So we look at the denominator, divide by 3, cube both sides. We get x equals 0. So we now know the location of our slope undefined. Is this going to impact our interval? Okay, here's the statement that we would have to write. The statement we have to write, if it's going to pass the test, is going to be f of x is differentiable, parentheses, 0 to 1. So this is the region we have to protect. This is the location of our sharp turn. Are we safe? Is 0 outside or inside this interval? It's outside. So what this tells us is that if there is a slope undefined at the endpoint, it's okay. It still will pass this test. Now, obviously, if this was between the endpoints, then we would stop the problem and say function not differentiable. We can't guarantee a slope if the slope isn't safe everywhere between the endpoints. But this is close, but it's still outside. So we can continue with the problem. We found our sharp turn. It didn't affect the interval. Both our conditions still pass. But it requires a little bit more work than what we did here, right? Here we made the statement. Here we got to go through derivative to answer that question about being a smooth curve. All right, so all that work was just to set up. Now we can move on to this step. Okay, we're going to take the endpoints, plug into the function, get the y value, get the slope. So we plug 0 in, we get 0. We plug 1 in, we get 1 to the 2/3, which is 1. Right. We find our slope, change in y over change in x. Okay, I'm going to use the space for 42 as well. Okay, we have this piece of the puzzle figured out. We have 1. We're going to set that equal to the derivative. The nice thing is we don't have to go through and find the derivative again, right? We already found it when we were going through our differentiable check. So we can just set them equal to each other. Set the derivative equal to the slope. Make it 1 over 1. Cross multiply. Divide both sides by 3, cube both sides. So this is a little bit more involved because we have to do some amount of work for that differentiable portion, but it's only for this type of problem. You only have to worry about doing that for anything that has like an odd root, like x to the 1/5 or x to the 1/7 or x to the 2/3. Those are the only types of problems you got to worry about sharp turns. Yes.
Okay, so when I did it, I like set the 2 over 3x to the 1/3 equal to 0.
Let's see. Oh, you said equal to 0? Is that what you did? Okay, so what we need to do is we need to set the derivative equal to the average slope.
Okay.
So the average slope is this f of b minus f of a over b minus a.
Oh, okay.
Now, we will set equal to 0 if it was, if we're trying to find critical points for EVT, then you would set the derivative equal to 0. But for MVT, we're not trying to guarantee a slope of 0, we're trying to guarantee a slope of 1, so we got to set equal to 1. Yeah. Yeah, it's a good question, because it's easy to get mixed with other process, right? They're all kind of similar, they're all kind of jumbled together, but yeah, glad you're asking that. Okay. So we reviewed 3.1, we reviewed 3.2. Tomorrow we'll do the same thing, but now we can move on to 3.3, which I think you will find easier because I think you've seen 3.3 already. Because we did particle motion, right? You remember we created a sign line for particle motion for velocity. You said velocity was 0. And then on the quiz, you were able to say, my particle is moving to the right because velocity is positive, moving left, its direction changes. Same process, just from a visual perspective, from a graphical perspective. Okay, so here's 3.3. Hopefully you guys have the notes. I'm going to have you guys copy this down first. Just some review with what the derivative represents. Derivative is the slope of a tangent line. So anytime we talk about derivative, that's a abstract word, right? But if we can think of derivative as slope, then it becomes more visual, more something that more it's a word that we can more concrete, right? We know what slope feels like in terms of steepness. Right, so derivative is just the slope of the tangent line to a function. If a function is increasing, what's common about the derivative at that point? We know increasing slope. Let me, sorry, I have another 6 here. We know that increasing slope is going to translate to positive derivative. So if a function is increasing, the common thing about the derivative is that we're going to experience positive derivative in all these locations. If a function is decreasing, remember, we only read the graph from left to right. Okay, we don't want to read the graph backwards. We always read the graph from left to right. So whenever the graph is decreasing, like in this interval, the common theme is that every point is going to have a negative derivative. F prime is always going to be less than 0 in all these intervals, at all these points. Okay. When f prime is greater than 0, our function is increasing. Okay, so I'm just kind of taking our statement and just kind of mixing it up here. So if this is true, then this must be true, right? If we have positive derivative, our function is going to be rising. If I have negative derivative, my function is going to be falling. If my derivative is 0, then that's slope 0. So slope 0 is where I'm going to not experience any steepness, right? It's going to be a level point. So at all these points, these are all slope zeros, right? So we have all these steps here, but I'm just going to jump to the example because we're going to see that it's the same process as determining when the object is moving right, when the object is moving left. It's just instead of velocity, we're saying f prime. Okay, so let's go to the bottom and look at example 1. So example 1 says determine the interval where a function is increasing, decreasing, locate relative extrema. So all this is going to refer to the derivative. So the derivative is going to help us gather information about rising and falling of graph. So we know the first thing we do is we always going to find f prime. So let's go through power rule, right? What's the derivative of the first term here? Good, yeah. The 3's will cancel out, right? Plus. Minus.
6.
Yeah, and then the constant goes away, right? So there's our derivative. And here, now we're looking for critical points. It's going to set the derivative equal to 0. Okay, so similar to EVT, similar to particle motion. It's like setting velocity equal to 0, right? That's always the first step if we're going to be creating a derivative sign line. So f prime, let me clean this up here. And when we find slope 0, it's going to help anchor our sign line a bit, and we're going to have some critical points to work with, and we know where our boundaries are for our increase and decrease. Okay. So that's factor this, right? Multiplies to be -6, adds up to be 5. Okay, well, multiplies to be -6, adds up to be 5. So 6 and -1. Right? Okay, solve for x. So these are the locations where our slope is 0. So remember, the purpose of this is to gather information about the behavior of the graph. We want to know where the graph is rising, where the graph is falling. And if we have a graph where slope is 0, kind of helps us separate those intervals a bit. So create our sign line. And just like with your velocity sign line, you're going to choose values in each interval, plug into the derivative, and use factored form to get quick information about your slope value. So I like to choose values that are as small as possible within each interval. So I'll choose -7 here. Into the derivative, so -7 plus 6 is negative, negative times negative is positive. I know my graph is going to exhibit a positive slope. And then to help with the visual, if you can draw an arrow, it kind of helps us visualize our graph is going to be rising in that interval. All right, so if the graph looked like this, we know that it's going to be this part of the graph. I'll choose a number between -6 and 1. I'm always going to try to involve 0 if I can. It's an easy number to test. So 0, and for x, I get 0 plus 6, 0 minus 1. Positive times negative is negative. So I know I have negative slope. My graph is going to be falling. I like to draw an arrow to indicate that my graph is falling in that interval. Helps give me a visual. And then to the right of 1, I'll choose 2. Plug 2 into the derivative, I get positive times positive, which is positive. So rises, it falls, it rises again. Now, we're going to write our intervals of increase and decrease, which is just basically pulling information from the graph. But yeah, so let's do that first, and we'll talk about the relative max, relative min in a second. So we'll say our function is increasing. Increasing is wherever we have positive slope, so our function is increasing. From -infinity to -6, right? Same thing how you did with velocity sign lines. Union or parentheses, or comma. Before, our justification was because velocity is greater than 0, but here we're going to say because f prime is greater than 0. Our function is decreasing from -6 to 1 because f prime is less than 0. So once you create the sign line, this is easy because you're just translating this into words. Okay. But let's talk about max and mins here. Well, first off, any questions here? Are we good? Increase, decrease, just pulling information from our sign line. Okay, so next thing is max and mins. Look at how the arrows are pointing here. The graph is going up and then it's falling down. So what can we conclude here? At -6, there must be a what? A relative max, right? We know there's going to be a peak for the graph somewhere because it's going to rise and it's going to fall. And at 1, there must be a relative what? Min, because if you look at the arrows, right, it's falling followed by rising. You can imagine a valley of the graph. It's going to be relative min. So we're going to write that out. We'll say relative max. Okay, we know there's going to be a peak of the graph. Now, we don't know the y value, so we can do this. -6, comma, space, just to indicate that we don't have the y value, but we can look for it later. And the reasoning is because these arrows, right? But we're going to put it into a wording that that College Board will encourage and accept. And it's because f prime changes from positive to negative. Okay. So that's the justification I'm looking for on the quiz, and this is the language you would use on AP exams as well if they're asking you to justify positive or negative slope, or relative max, relative min. Okay, relative min. At 1, we don't know the y value, so we'll leave that space open. Because f prime changes from what? Negative to positive, yeah. So on the quiz, I'm looking for these justifications. All right. So it's basically always going to be the same wording. It's just that based on the interval. Now, not every sign line is going to produce every one of these 4 statements, right? It's possible that we may not have a relative max or relative min, and maybe there's only increasing and not decreasing, but at least here we see all the different possibilities.
So is that just like the answer? Like all that together? Or...
Yes, this is answering all the questions about increase, decrease, and then locating relative extrema. And then on the quiz, I'm going to say justify your answer.
Okay.
And justify your answer is with all these because statements I underlined. Yeah. But I feel like if you can get to this point, then translating from here to here is easier, right? This is not a difficult process. But if you guys can put a star next to these 2 here, I don't know why, but students every year will justify these statements, but they will leave these blank. I don't know. It's like it happens every year. But I'm going to say justify every statement, so expect to write because statements every time I ask you for a characteristic. Right? Yeah, I'm not. I don't know why it happens every year, but so I think that's all we need to get through for today. There's homework from 3.3. I have that link under today's on my website under today's date. So just over 3.3 tomorrow. I want to do the same thing. I want to review 3.1, 3.2, 3.3, and then we can talk about 3.4. And then Monday will be full review, Tuesday review, Wednesday review, and Thursday quiz. Next Thursday quiz. All right, if you're on Teams, you're free to go. Have a great day, guys.